Chapter 8, the quantum mechanical model of the atom. I love this quote from Niels Bohr, who was involved in developing quantum mechanics. Anyone who is not shocked by quantum mechanics has not understood it. So this is a topic that you are not going to understand. I don't completely understand it. Einstein didn't understand it, right? So we're just going to try to learn enough about it that we can say, yeah, okay. If you say that, sure, we'll go along with that. That's kind of cool, but what? That's just how it is. Sorry about that. Okay. So this all started in the beginning of the 20th century, early 1900s. Before that, everyone believed that all physical phenomena were deterministic, meaning its current condition allows us to predict what's going to happen to it in the future. You throw a ball, you know the trajectory, the effect of gravity, wind resistance, all these different forces. You can predict what's going to happen to the ball. It turns out that that doesn't work for subatomic particles. If you shoot an electron down a path and measure where it lands, and you shoot another electron down the same path in the same conditions, it's most likely going to land somewhere else. Baseballs don't work that way. Okay? Pitching machine, it comes the same place every time. So this is a little disturbing. And this is because the electron is part of the absolutely small or quantum world. These are particles that are so small, they have a whole different set of rules. So they behave completely differently than the large or macroscopic world that we can see. So the crazy thing about these absolutely small particles is they can be in two, actually, or more different states at the same time. And that's not states like I can stand with 1 foot in California and 1 foot in Arizona. Okay, that's obviously not what we're talking about. But an electron can be a wave and a particle at the same time. Or a radioactive nucleus can be emitting a particle and not emitting a particle at the same time. And that sounds impossible, doesn't it? It is impossible with real life visible objects. Not that electrons aren't real life, but we can't see them, so they kind of seem made up. They are incredibly small. So I like this one. A single speck of dust has more electrons than the number of people who have ever lived on Earth. What? That's a lot. A lot of electrons in this little speck of dust. And you think about it, it's even crazier. Most of the volume of that speck of dust is empty. The electrons take up very, very little of its space. I mean, these are just mind-bogglingly small. Why do we care about this? Because the behavior of electrons determines a lot of the behavior of atoms, and we do care about the behavior of atoms. We want to know, is this thing going to dissolve in water? Is it going to stand up to heat if I put it in the oven? Those sorts of things. So we can't directly observe electrons in the atom. And even if we could, because it's part of this absolutely small world, if we observe it, then we change its behavior. You're like, well, are electrons alive? How do they know that we're observing them? Yeah, that's one of those things that's hard to understand. Of course, they're not alive. Even shining a light on the electron will cause it to be one thing or another, because when we're not observing it, it's in this superposition. So, you may have heard of Schrodinger's cat. This was a thought experiment. No cats were harmed in this experiment because it was just in somebody's mind. The point of this is that it demonstrates how quantum strangeness, quantum behavior, does not transfer to the macroscopic world. The rules are just totally, totally different.
So without further ado, we present Schrodinger's Cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they'd react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead. And an equally good chance that the vial hasn't been broken and the cat's just kicking it, wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrodinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrodinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
So there's some quotes here. Niels Bohr, this is the quote I read at the beginning. Anyone who is not shocked by quantum mechanics has not understood it. Schrödinger, Schrodingers Cat, wrote about quantum mechanics. I don't like it, and I'm sorry I ever had anything to do with it. This was a huge discovery. And he's like, nah, I wish I'd never done that. Albert Einstein attempted unsuccessfully to disprove quantum mechanics until he died. He didn't like it either. But he couldn't prove that it was wrong. So we're kind of stuck with it. So the quantum mechanical model explains how electrons exist and behave in atoms, and it helps us to understand and predict the properties of atoms that are related to the behavior of atoms. And so it can answer questions like, why are some elements metals and others are nonmetals? Why do some elements gain one electron when they make an anion and others gain two? Why are some elements very reactive and others are practically inert? And then there's a lot of other things, especially periodic patterns in the periodic table, that can be explained by quantum mechanics.